Hello and welcome to Math 138. Today we'll be starting with Chapter 2, Section 2. Okay, it's the first section in our syllabus. We are in our chapter of limits and derivatives, and we'll be looking at the limit of a function. Okay, so we're going to be looking at limits in general and numerical and graphical methods for computing these limits. Okay, so these are just generic limits, and we're looking at the graphs and graphs. We're looking at tables of the graphs to look at how to come up with the limit of a function. So we start off with our first example. The behavior of the function f defined by f of x equals x squared minus x plus 2. Okay, so there's our function. And we're going to be looking for what's happening to that function for values of x near 2. Okay, so if we're writing the notation for this, we would say limit as x approaches 2, and we could put our function in there. We could just say f of x, or we could say limit as x approaches 2, and we could just put the actual function equation part. Okay. All right, so let's see what happens. I like to take a look at the graph of this function. Okay, it's a quadratic, so it'll be a parabola, and we're going to look at what's happening near x is 2. Okay, so I went ahead and I graphed this. I used Desmos. Okay, for those of you that know Desmos, very useful graphing utility. If you're ever curious and you're on like a homework or something and you want to find out if you're just doing practice problems, I would recommend desmos.com. Type in the equation and then it graphs it for you on the fly. This is what it looks like. Okay, so as x is approaching 2, so if we're looking at our x-axis, so we're looking at 2, what's happening as x is approaching 2? What's going to happen to the function, right? So on the function, it appears that as x is approaching 2 from the left, right, this is going to be going like that. As we're approaching 2 from the right, we're approaching it like that. And it looks like our function is approaching, and we could, eyeball this and get a pretty accurate result. It looks like it's approaching 4. Right? So if this is the location where it's getting close to, it looks like we're approaching 4. Okay, so as x is approaching 2, our function is approaching 4. Now, when we go to look at this in a table setting, okay, the table will look like this. So what we'll do is we'll end up picking values to the left of 2. So if you're looking at the graph of this, you want to be approaching it from the left. So any values like 0, 1, and then you can say like getting closer to 2, 1.5, 1.7, 1.8, 1.9, 1.99, right? As you get closer and closer to 2. Now from the right, you could put values such as 4, 3, 2.5, 2.25, 2.1, 2.01, okay, so on and so forth. And that's what we're seeing here in the table, right? Values starting at 1, 1.5, 1.8, 1.9, all the way up to 1.99. Looking at the y values, Okay, so how do we get the y values? Just plug these in, right? Plug in the x values into the function. It appears that they're getting closer and closer to what we said in the graph, right? We're getting closer and closer to 4, right? On the flip side, from the right, starting at 3, getting closer to 2, 2.5, 2.2. Okay, and it appears our y values are getting close to 4. Okay, so it's safe to say that the function is approaching 4. Okay, and so for this we would say the limit of the function as x approaches 2 is equal to 4. Okay, and that's how we would write it in notation form. Okay, so a pretty straightforward example. Okay, so the limit of a function. Okay, in general we would use this notation. Okay, the limit as x approaches a of f of x is equal to L. Okay, and that's how we would express it, right? The limit of f of x as x approaches a equals L. Okay, we can make the values of f of x arbitrarily close to L. Okay, as close to L as we like by taking x to be sufficiently close to a on either side of a but not equal to a. Okay, and we could see what the trend looks like. We could do what it approaches from both sides of a, from the negative side of a, from the positive side of a, and then we could see what the limit of the function approaches. An alternative notation for the standard notation we would say is f of x, and you'll see an arrow symbol. Okay, so f of x approaches L as x approaches a. Okay, so that's another alternative to writing the limit. Okay, so let's take a look at these three scenarios. Shows the graph of three functions. Okay, it says note that in part C f of a is not defined, and in part B f of a is not equal to L. Okay. Okay, in each case, regardless of what happens to a, it is true that the limit as x approaches a of our function is equal to L. Okay, so let's take a look at that. Okay, the limit is L in all three cases. Okay, so here it appears it's a regular polynomial graph, like the one we had in our first example. As x approaches a, yeah, the function is approaching L, right? Okay, no big surprise there. Let's take a look at B. Notice in B, the function may not be easy to see in the picture, but there's a hole here. There's like an open circle at A. Okay, and actually it's defined over here. Okay, so the dot here, that's where it's defined, and there's an open circle where A is on the function. Okay, so in that case, that's another case where we have the function, it appears to be approaching L. Okay, and that's true because if you're approaching A from the left, it appears as if it's going towards that value. And same thing from the right. If you're approaching A, it appears as if it's going to L. Okay, so it's safe to say that the limit there is L. Okay, and that's true even though it's not defined at that point. It's defined to be somewhere else. The limit would still be that same value. Okay, and then here there's another open circle at A. Okay, so it's not defined anywhere. Okay, but the limit would still be, it would still be L. Okay, because it looks like the function is approaching L from both ends, from both sides. Okay, guess the value of limit as x approaches 1 of x minus 1 over x squared minus 1. Okay, so one of the things to note is if we have a rational function like this, if you were to graph this function, the graph would be not defined at x is 1. Right? If we plug in 1 and we get a y value, we would get a 0 over 0, which is an indeterminate form, has a 0 in the denominator, not defined. Right? So, but that doesn't matter. We could take a look at the graph, we could take a look at the table and see if it's approaching any particular value in general. Okay, so here in the table form, if we're looking to the left of 1, like 0.5, 0.9, 0.999, okay, it appears to be approaching, looks like a value of 0.5. Okay, it looks like you see the decimal here. The zeros after the 5 increase as long as you add another 9 at the end of the decimal here. Okay, it's safe to say from the right side as we get closer to 1, so starting at 1.5, 1.1, 1.01, all the way to 1.0001, it becomes 4.4999. That trend is going to keep going as long as we keep adding zeros here, we keep adding 9s in here. So it's safe to say that the limit of this function, this rational function, is approaching 0.5. Okay, so that's based on the table. Alright, and if we look at the graph of that function, okay, it looks like the graph is defined everywhere except 1. Right, so you'll have an open circle where 1 is, but the function will be approaching 0.5. Okay, now it says here, let's change the function slightly by giving it the value 2 when x equals 1 and calling the resulting function g. Okay, if that's the case, then that means when x is 1, the function will be defined and it'll have a value of 2. Okay, but it doesn't matter if you're looking at the limit question. The limit will still be the same, right? The limit of that function, even though it's defined to be 2 now, when x is 1, you're looking at the general trend of the function. You don't want to look at what the function is defined at a particular point. You want to look at the general trend for that function. And all the signs point to that limit is approaching 0.5. Okay, so that's what you want to look at when you're doing problems like this. What's the general trend for that function? Okay, that's what we just talked about. Let's take a look at another example. Estimate the value of, okay, limit as t approaches 0 of square root t squared plus 9 minus 3 all over t squared. Okay, so you could do is You could try to graph that. Okay, you could also come up with a table. Let's take a look at the table. Okay, so here we have a table. Okay, listing values of the function for several values of t near 0. Okay, starting at positive and negative 1. Okay, gave us 0.16228. Then we got a little closer, plus or minus 0.5, 0.16553, plus or minus 0.1. Okay, we got a little bit closer to 1.16662. Get even closer to plus or minus 0.01, and we're at 0.16667. Okay, so it appears in all likelihood this is approaching a value of 1/6. Okay, those that know your values of your fractions. Okay, 1/6 is what it appears to be approaching. Okay. And there's ways to show the limit of 1/6. We'll come back to it. So later on we'll see how we could come up with a value of 1/6 even without doing a table or a graph. Right? There are ways to circumvent just the plugging in of a 0 into our function. Yes, the value of limit as x approaches 0 of sine x over x. Okay, so we can look at the graph of that. Okay, if we graphed y equals sine x over x, this is what the graph would look like. Okay, now obviously at x equals 0, we'd have a case of 0 over 0, which will be undefined. Okay, so notice that's why we have the hole there. Okay, but in all likelihood, right, the general trend tells us that the limit of this function is approaching 1. Okay, we could do a table. Okay, and if you do the table, you'll see the general trend. Okay, as we get closer and closer to 0, our function gets closer and closer to 1. Alright. Again, any questions with this, you could bring it up. You could email me. You could bring it up during class. But yeah, any questions as well, just let me know. Okay. Alright, let's take a look at this one. And investigate the limit as x approaches 0 of sine of pi over x. Okay, so the sine of pi over x, let's take a look. We could graph that. Okay, this is what the graph of it would look like. When it starts to go back and forth and have this almost like a slinky pattern, that's called oscillating behavior. Right? The function is oscillating between some values of several values on the y. Okay, and when that happens, when you have oscillating behavior, you're not going to have a limit of a function, right? That we often say when there's oscillating behavior, the limit does not exist. Okay, sometimes you'll see it abbreviated DNE for does not exist. Okay, so that'll happen anytime you have oscillating behavior near where your limit is. Okay, so as we approach 0, you'll see this wild fluctuation Find the limit as x approaches 0 of x cubed plus cosine of 5x over 10,000. Okay, so if we plug in our 0, right, we can see what the value is. We would have 0 cubed plus cosine of 5 times 0 over 10,000. 0 cubed is 0. Now 5 times 0 is 0. Cosine of 0 would be 1. So we have 1 over 10,000. And that would be the limit of this function. Okay. The Heaviside function h is defined by, okay, so h is defined as 0 if t is less than 0 and 1 if t is greater than or equal to 0. Okay, so if we look at the graph of that, let's do a graph real quick. So the graph would basically be it says 0 if t is less than 0. So our t's are here, and h of t would be here. So for less than 0, it'll look like this. And then if t is greater than or equal to 0, then it would be at 1. Okay, so then we'd have closed circle going like that. So if we looked at the limit of this as t equals 0, right? Like, let's say the problem is find the limit as t approaches 0 of h of t. Okay, so as we're approaching 0, well, we got from the left, it looks like it's approaching 0. From the right, it's approaching 1. Right? From the left, it's approaching 0. From the right, it's approaching 1. So they're approaching two different values. Okay, so therefore, because there's no agreement in those, this will be a does not exist. Right, so that's one of the lessons to take out of this. For a limit to exist, the function must approach the same value from the left and the right. It has to approach the same value from both sides. Okay, and that brings us to our mini topic here, one-sided limits, right? So if we said limit as t approaches 0 from the left, and that's what that means, 0 with a little minus, that's from the left side of, okay, this would be the minus side of 0. This will be the plus side of 0. Okay. This will be equal to 0. The limit as t approaches 0 from the right of our function, this will be equal to 1. Okay. And so because those two limits do not agree, the limit as t approaches 0 for our function does not exist. Okay, so one-sided limits. Okay, and we just talked about that. Heaviside function. Okay, the symbol t approaches 0 minus indicates we consider only values of t that are less than 0. And then likewise, t approaches 0 with the plus indicates we consider only values of t that are greater than 0. Okay, so notation-wise, this is telling us the limit as x approaches a from the left, right? Because we got the little minus there. And this notation, the limit as x approaches a from the right, okay, the right-hand limit of f of x. All right, questions? Okay, any questions, just let me know, email me, etc. Okay, and this is what we mentioned earlier. The limit as x approaches a of our function is equal to L, right, our limit, if and only if the left-sided limit, right, x approaches a from the left, and the right-sided limit, x approaches a from the right, are both equal to L. Right? So those two limits have to match in order for us to have a general limit as x approaches some value. Okay, one-sided limits from a graph. Let's take a look at this graph. Let me make it a little bigger. Okay, the graph of a function is shown in this figure. Use it to state the values if they exist of the following. Okay, so let's do this. Limit as x is approaching 2 from the left of our function. Okay, so all this is g of x. Right? So this curve, all this dot. Okay, so limit as x is approaching 2 from the left. Okay, so here's 2. From the left of 2, looks like we're approaching 3. Right? Okay, limit as x is approaching 2 from the right. Okay, as x is approaching 2 from the right, it looks like it's approaching 1. And then the limit as x is approaching 2 in general. Okay, so because we have this disagreement, right, of both sides, this would be it does not exist. Okay, let's take a look at our next set. Limit as x is approaching 5 from the left. Okay, so as x is approaching 5 from the left, it looks like the function is approaching 2. Limit as x is approaching 5 from the right. Okay, looks like it's also approaching 2. Limit as x is approaching 5. Okay, so both sided limits agree, right? The left-sided limit and the right-sided limit, they're both 2. So here, the function is approaching 2. Okay, and notice it's approaching 2 even though at x equals 5, the limit is defined as, looks like to be a little bit more than 1. It looks like 1 could be a little bit more, but it's defined to be at this point, right? Not at 2. But it's okay. You're looking at the general trend for the function. Okay. Okay. Right, and we talked about that. Despite this fact, notice that g of 5 is not equal to 2, right? We just mentioned that. Okay. Good. Okay, find the limit as x approaches 0 of 1 over x squared, if it exists. Okay, so you could look at the function. We could look at the graph of the function. Okay, notice as x approaches 0, we got this, this will be approaching what looks like a vertical asymptote, right? Because notice at 0, when we plug 0 in here, we get an undefined. Okay, so that's always a big clue to tell you that, okay, the function is not going to exist there. Okay, so that's one key. If we looked to plugging in values, okay, as x approached 0, you'll notice that the values of the function will get really, really huge. Right? If we did a little table here, like an xy table, if we plug 1 in, right, 1 over 1 is 1. If we plug 2 in, well, we would go farther away, but let's say we get closer to 0. So if we plug in, let's say, a half, and then we have 1 over a half squared. Half squared is 1/4, so 1 over 1/4 would be 4. Okay, if we did something closer, like 1/10, 1 over 1/10 squared. 1/10 squared is 1/100th. 1 over 1/100th would be 100. Okay, so it looks like the limit for this, as x gets closer and closer to 0, right? Because as I keep shrinking this is going to keep getting larger and larger. Like if I did 1 over 100, that would end up giving us 10,000. Okay, and this works the same whether it was positive or negative. Okay, so we see that the numbers are, the function is going to keep growing and growing and growing. Right? It's not going to approach a single number. It's just going to keep going out of control. Okay, so then we would say for this function that the limit does not exist. Okay, so we would say limit as x approaches 0 of 1 over x squared does not exist. Another way to think about this is it's going off to infinity. Right? This is an infinity case. Right? This is going to go shoot upwards towards infinity. Okay, so another way to say infinity is the limit does not exist. There's no limit to this growth. All right, any questions? Just shoot me an email. And that's it for the lesson, okay, for 2.2. All right, any questions, just shoot me an email or bring it up during class. Have a good day, have a good night. We'll see you soon.